All right. Implicit differentiation is a different kind of differentiation than the kind we've been doing so far. And by implicit, we mean equations that aren't necessarily functions. So examples. If you look at x squared plus y squared equals 1, you should probably recognize that equation. It's the equation for the unit circle. That's what the graph of it looks like. X cubed plus y cubed equals 6xy is that sort of loop-de-loop looking curve that's called the folium of Descartes. And something like y sine x equals x cosine of y, well, that's just a crazy looking graph. But it is a graph. So I'm using the word equation because the one thing all these curves have in common is that they're not the graphs of functions, right? None of these are the graphs of functions. So far, we've been talking about derivatives of specific functions, but these are equations. They're not functions. But you can still picture, look at the unit circle, you can picture a tangent line to it, right? You know exactly what a tangent line to that thing should look like. Same with the loop, the folium, the second one. You can still picture a tangent line moving around that thing. Same with the third graph, the crazy one. So there is a y prime. There is a derivative of that function with respect to x. To do the derivative of 1, we could split it up into the top half and the bottom half. The top half would be square root of 1 minus x squared, and the bottom half would be negative square root of 1 minus x squared. And then we could just do the derivatives of those as two separate things. So we could do that the old-fashioned way by just splitting it up into two curves that are functions. If you look at number 2, though, it would be extremely difficult to write that as y equals something. You'd have to split it up into like 4 or 5 different curves and use some kind of crazy cubic formula. So possible but unrealistic. The third one would be absolutely impossible. Imagine trying to solve that equation for y. Go ahead and try. You literally cannot do it. It is not doable algebraically. So when we say implicit, we mean as opposed to y equals f of x. That's an explicit function of x. Y is some function of x. Whereas here it's more of just a relationship between the two variables. That's why we call it an equation, not a function. Some notation. dy dx, we've seen this before. That's called Leibniz notation. Means the derivative of y with respect to x. So if y were just sine of x, then dy dx would just be cosine of x. Sometimes it's quicker to write, and I like to just write y prime. So instead of f prime, we just have y prime is just the derivative of y with respect to x. In implicit differentiation, we take an equation like the three we're looking at. We take the derivative of both sides. So that's an algebra move. We can do whatever we want to both sides of an equation. Taking the derivative is just another move. And then the tricky thing is we treat y as a function of x. So even though we can't write y as a function of x, we treat it as one and we say, okay, if it were, what would happen? And that involves using the chain rule. So here's the first example. X squared plus y squared equals 1. So we're still looking for the slope of tangent lines. The thing we get at the end of this is going to involve x's and y's, but it is going to be y prime equals something, and that something is going to give us slopes of the tangent line at points along the curve. So when we take the derivative of both sides of the equation, we're still treating x as the variable. So like the derivative of x squared is still just 2x, but now we're treating y as a function. So there's the move. So here's the important thing. The derivative of y squared isn't just 2y because y is a function. The derivative of y squared is 2 times y times y's derivative. Now, we don't know what y's derivative is, so we're just going to call it y prime. My example is picture if y were something like sine of x. Then if I ask you, okay, what's the derivative of y squared? Well, y squared would be sine squared. So by the chain rule, the derivative of y squared would be 2 times sine of x times cosine of x, right? So it would not just be 2y, it would be 2y times y prime. So that's the derivative of y squared here. So you have to imagine y as a function and use the chain rule. So we just go across on both sides. The derivative of x squared is still just 2x. The derivative of y squared is 2 times y times whatever the derivative of y is. We don't know that. We're trying to figure it out. So it's a weird algebra thing where it's like you create the variable. The thing we're trying to find is y prime, but it pops out of there just by using the chain rule. And then the derivative of 1 is, as always, just 0. And now we actually have to do algebra. So we haven't had to solve a lot of equations in this course, but now we do. So we have to take that little relationship and just solve it for y prime. So that was the calculus. The rest is just moving stuff around the board, algebra. Subtract 2x from both sides. Divide by 2y. Simplify. Y prime is negative x over y. So so that derivative has a y in it. We started with an implicit equation, right? That had x's and y's all mixed together. We ended up with an implicit equation, and that's in fact going to happen. So what that says is if you're at some point on the unit circle, the slope of the tangent line at that point is just negative the x coordinate over the y coordinate. So here's the unit circle and some tangent lines to it. Look at the point in the first quadrant, square root of 2, square root of 2. So that's where theta would equal pi over 4. The tangent line there looks like, looks like it has slope negative 1. And if you just think about, okay, the x and the y coordinate are the same at that point. So negative x over y is just negative 1. Same with if you look over in the second quadrant, negative x over y should just be 1. And that's what the slope of the tangent line is, right? So it's different than what we've been doing, but it's very useful, especially if you have to take Calc 3, you deal with equations of 3, 4 variables, right? And then you have to do everything like this. Okay, so here's the second one. All we're doing with this is examples for now. We'll see where to use it next time. So that second curve we saw, x cubed plus y cubed equals 6xy, that loop-de-loop looking thing. First step is always the same. Just do the derivative of both sides of the equation. So on the left-hand side, it's going to be a lot like the last one. We're just differentiating x cubed and then y cubed. On the right-hand side, x times y is a product. So we have to use the product rule on that. Again, I think it's helpful just to use an example. Imagine if y were sine of x. Then if I asked you to do the derivative of x times sine of x, then you would know that you needed the product rule. You don't just multiply the two derivatives together, right? You have to use the product rule, and that 6 just comes along for the ride. So the 6 I'm leaving on the outside because it just comes with. So we have 3x squared plus, again, the derivative of a function cubed is 3 times the function squared times the derivative of the function. So the derivative of y cubed is 3y squared times y prime. And then the right-hand side is the product rule. So the first times the derivative of the second. Now, if it's just y, the derivative of y is just y prime. You don't need the chain rule for that. So if you're just looking for the derivative of y, that's what y prime is. And then plus the derivative of the first function, well, the derivative of x is just 1 times the second. So we're not done. We have to solve that equation for y prime. So however you do that, you should be able to handle that. Let's simplify it. So just redistribute that 6 back in there. And now to get y prime by itself, we need all the stuff with a y prime in it to be on one side, and all the stuff without a y prime in it to be on the other side. So I'm going to take that 6x y prime and throw it over on the left side. And then I'm going to take that 3x squared and throw it over on the right side. So I kind of did two moves at once there. I subtracted 6xy prime from both sides, so now it's on the left. And I also subtracted 3x squared from both sides, so now it's on the right. So I hope that's okay. I just did two things at once. And the point of doing that, of grouping it like that, is now I can factor it. So anytime you have more than one term that has a y prime in it, the only way to get it by itself is to factor. The only way to do that is to have it all in one side. When you take the y prime out, you're left with 3y squared minus 6x on the left-hand side. And then we divide both sides by that, and we're done. So finally, y prime is 6y minus 3x squared over 3y squared minus 6x. So started with a fairly complicated equation in x and y, got a fairly complicated y prime with an x and a y. So you'd pick a point on the curve, and then the slope of the tangent line would be determined by this. You'd take, so it involves the x coordinate and the y coordinate of that point. There's just a function, there's its graph to remind you, and there's y prime. I'm sorry, it's not a function, it's an equation. 3, 3 happens to be a point on there because, okay, 3 cubed plus 3 cubed equals 6 times 3 times 3. So I just happen to know that that's a point on the curve. And in fact, it's the tip of that loop. So if you look at the point 3, 3, you would think that the tangent line is perfectly diagonal, and it is. And it's diagonal going downwards, so its slope is -1. So you just punch 3, 3 into that y prime. You get 6 times 3 minus 3 times 3 squared over 3 times 3 squared minus 6 times 3. So those are just negative of each other. So that slope indeed turns out to be -1. And that's what that looks like. So verify that that looks right? That looks like a tangent line. So we still have the case where, at those flat spots, we do have tangent lines that are 0. If you look right at the origin, the graph crosses itself. So there's actually 2 tangent lines there, which is a little unusual. One's vertical, one's horizontal. That's the kind of thing you're going to get more into in Calc 2. These are called parametric equations, or equations that you could think of like just traveling around the plane in time, where it just loops around and makes some sort of weird shape. So I just want you to see that it looks right and that the system works. We are still just finding slopes of tangent lines. Okay, let's do the third one. It looks crazy, but really the math is going to shake out in exactly the same way as the previous one did. So the left-hand side is y times sine of x. Both those things are functions. We're going to have to use the product rule. The right-hand side is x times cosine of y. Both those things are functions. We're going to have to use the product rule. With that cosine of y, remember that's a function of y. So think about that as like cosine of x squared. The derivative of that would be negative sine of x squared times 2x. So there's going to be, the chain rule is going to make there be a y prime that hops out on that side. So here we go. Just doing the derivative of both sides of an equation. That's a legitimate move. All right. So here's the product rule. It says, okay, it's the first thing, which is y times the derivative of the second thing. The derivative of sine of x is still just cosine of x, plus the derivative of the first thing, which is just y prime. Remember, the derivative of y doesn't involve the chain rule. It's just y prime, times the second thing, which is sine of x, equals, okay, the first thing, which is just x, times the derivative of the second thing, which now we need the chain rule because this is the cosine of a function of a function. The derivative of cosine of y is negative sine of y times whatever the derivative of y is. We don't know, so we have to just call it y prime. So you see what I'm saying? It's like an algebra equation where you're responsible for like generating the variable that you're solving for, because it just occurs naturally because of the chain rule. And then plus the derivative of x, which is just 1, times cosine of y. So product rule on both sides. We can clean that up a little. So just writing that as negative x sine of y, y prime plus cosine of y on that right side. And you'll notice you have to do this next move a lot. You have two terms that have a y prime in them, so those both have to be on the same side. So again, I'm going to put them on the left side and everything else on the right side just because I think that looks right. So I've done two moves at once again. I took that negative x sine of y times y prime and I added it to both sides. So now it's on the left. That way's left for you. And I took that y cosine of x and I subtracted it for both sides. So now it's on the right. Right, so that's what that looks like. And right, it's the same as the last one. Now that we have everything with a y prime in it on the left-hand side, we can factor it out. So factor out the y prime. What's left over is sine of x plus x sine of y. And now divide both sides of the equation by that, and you're done. So finally, y prime is cosine of y minus y cosine of x over sine of x plus x sine of y. All right, so I'm not going to show you an example because this is a crazy graph. So for any point that happens to be on that initial weird graph, you take the x coordinate and the y coordinate, you punch them into this thing here, and that gives you the slope of the tangent line. So even though it's a weird looking graph, it's certainly not the graph of a function. Your calculator wouldn't know what to do with this. You can still picture tangent lines moving around it at any point on the curve. The slopes of those tangent lines are given by this thing here.